All right. I'm going to write down an equation. Those of you who have read the chapter already have seen this equation already. Right? How many of you have already read the chapter? Okay. This is basically the only equation for the whole chapter. But depending on the situation, the specifics of the situation we're talking about, the D's and the M's, and maybe even the thetas, means something a little different. So way back at the beginning of the semester, when we were talking about sound, we made the point that sound is a pressure wave that is carried through the air, right? Waves have peaks and troughs, right? So if we were graphing pressure versus distance, this is what a sound wave would look like. Does this look familiar to everybody? Everybody remembers what we covered at the beginning of the semester? Maybe? Yes. Okay. For light, our idea about how it travels is exactly the same, except that instead of air pressure, what we're actually measuring is strength of the electric field. So the strength of the electric field of a photon varies as it travels through space. We use exactly the same lingo, though. The distance between peaks is a wavelength. So all of the stuff that we talked about at the beginning of the semester with waves, we're going to talk about light in that context now. So we know from earlier that if we match, if peaks of two waves match up, then we have constructive interference. Also, we know that I cannot draw. Right, so if we added this pink wave and this blue wave, we would get a wave that's got even higher peaks. Right? Maybe like the green dots here. However, if we're matching peaks with troughs, right? So here's one wave, one photon, and then if a second photon is, let's see if I can do this. Oop, nope. There we go. So if the electric fields of two different photons are like so, then the net effect is that there is no electric field at that point. So no electric field variation means no light. This is destructive interference. that in mind, let's take a look at some geometry. Before we talk about the double slit, let's talk about a single slit. Alright, so there's a slit that light can come through on the left. There is a screen on the right which can detect photons. And let's consider two cases. One photon barely makes it in the top of our gap, and one photon barely makes it in from the bottom of the gap, like so. Thinking back to our discussion about sound waves at the beginning of the semester, if the distance, let's call these R1 and R2. If R1 minus R2 is equal to half a wavelength, then at the point on the screen where they both intersect, we will be matching peaks with troughs, and we will get destructive interference. However, if the difference is equal to a whole wavelength, then that's constructive. Everyone remembers this bit? Yes? So far I haven't said anything new? Okay. Let's talk about the dimensions of this experiment. We'll have a distance L between the slit and the screen. Yeah, R1 and R2 are the distance the photons are actually traveling. Distance h here, and the slit itself is a distance d wide. So far, so good, everybody? So if these are the dimensions, then we can use the Pythagorean theorem to get these distances, right? Or we can use some trigonometry to get these distances. There are some useful approximations that we make. First of all, the distance d is small compared to the distance L, which means that the angle that these two photons travel, are angled at, they're basically the same, right? So the width of the slit is going to be on the order of 1/10 of a millimeter, whereas the length is going to be on the order of a meter. So yeah, there's the vertical distance that these photons travel is basically h. I mean, because h plus d is basically h, and also it's much smaller than L. So Sorry, I lost my train of thought for a moment. Okay, sorry. So, what is the difference in distance that these two photons travel at this point? How do we get at that? People have read the book, so I assume you have some idea. Right? How do we calculate this distance? Nobody? Yep, we can definitely use the Pythagorean theorem. So we could say R1 is equal to square root of L squared plus H squared. R2 is equal to the square root of L squared plus H plus D, quantity squared. So how do we take the difference of these two now? Is that a trick question? No, it's not a trick question. Right, but they're both under square roots, and square roots don't distribute over addition, right? So if we do, R2 minus R1, I mean that's as far as we can go, right? There is a trick that we can use here, though. And you probably encountered this for one day in an Algebra 2 class and then never thought about it again. But if x is small, then the square root of 1 plus x is approximately 1 plus x over 2. We can apply that here. Let's factor out an L squared from the radical. So we can say this is approximately L times the square root of 1 plus h squared over L squared. And then we can use this approximation trick. So this is approximately L plus, and then h squared over L squared, right? Half of that times L. So we get plus h squared over 2L. And this becomes approximately L plus h plus d squared over L squared. we get exactly the same sort of results. Now we can subtract them, right? Subtract R2 minus R1. The L's cancel. The h squared term cancels, because when we expand this h plus d squared binomial, we get h squared plus 2hd plus d squared. And everything cancels except for the 2hd plus d squared. Now we have to do a little bit more work. Let's split this into two terms. Right? So we have a 2hd over 2l. Well, the 2's will cancel. And if we do a little commutivity, we have d times h over l. And we have to pull a trick on the second term. Right? So if d is small compared to l, then d squared is like super small compared to l. Right? It's so small that in fact we say it's approximately 0.
Why is the d separate from the h over l?
I just chose to write it that way because if we look back at our picture, h over l is sine theta. I don't know if that gasp was genuine, but I appreciate the drama. All right. So far, we've actually analyzed this as if it was two separate slits. So if we stopped right here, and if we said photons can only come in at the very top or the very bottom, that is basically like saying that we have two slits. Right? One here that's just big enough for a top photon to get through, and one here that's just big enough for a bottom to get through, in which case our D becomes the space between the two slits. So let me restate that. Right? So we are not done with our analysis yet. But if light can only come through the very top or bottom of this slit, that's basically like saying we have two slits. So for two slits, to get constructive interference, we need d sine theta to be equal to some whole number of wavelengths, right? So what's on the left side is the path length difference between the two photons, and what's on the right side is our condition for constructive interference. This is not the way that your book justifies this formula, by the way. So the book uses some trig ratios and similar triangles to show that the path length difference is d sine theta. We took the hard way around because when I was asking for feedback, the only thing I heard was Pythagorean theorem, so we went Pythagorean theorem. All right. For a single, what's m again? M is some integer. Right, where here the positive numbers will correspond to bright fringes above the slit, and the negative ones will correspond to bright fringes below the slit. We have other comments or questions. I know that we've definitely got some people who are scratching their heads, so let's bring those questions out to the forefront. Nothing? Okay. I'm going to move to a new board. We're going to be a little more explicit in illustrating the single slit case. So on the last board we did the double slit case, but if we really have a single slit, right? We did the analysis for the very top and very bottom photons, right? But these aren't the only photons, right? There are also many in the middle. And if these two photons differ by a full wavelength, then that must mean that like these two here differ by a half wavelength, because they are half as far apart as the ones on the far end. And if that's the case, then we can imagine all of these rays coming through here. Each one of them is going to have another one that it destructively interferes with, because this whole middle part is also filled with light rays. So like this top one will cancel with this middle one. The next one down will cancel with one that's just below the middle. right? And then so on and so forth. They will all cancel. Each one of them will have a complementary light ray that it cancels with. And so for a single slit, we have exactly the same equation. Except this doesn't provide constructive interference in this case. It provides destructive interference. So in the double slit case, this formula predicts the location of bright spots. In the single slit case, it predicts the location of dark spots. How many slits do you think that we could have? How many slits do you think we could play this game for? Yeah, as many as we want. That is exactly right. And in fact, much of modern optics relies on what's called a diffraction grating, where it is many, many slits, a very small distance away from each other, right? And we use that overlapping series of constructive and destructive interferences to get all sorts of optical properties. For example, well, actually, before we say for example, we'll say that for a diffraction grating, we actually have exactly the same controlling equation. And I also accidentally pushed the button on my stylus. For the double slit case, d is the distance between the two slits. For the single slit case, this is the width of the slit. And for the diffraction grating case, this d is the distance between any two slits. Like it's the distance between slits on the grating. When you buy a diffraction grating, it's commonly quoted in like lines per centimeter. So for a little money, you can easily buy a 2,000 line per centimeter grating. Well, that means that d is 1/2000th of a centimeter. Right? If there's 2,000 lines per centimeter of the grating, then the distance between them can only be 1/2000th of a centimeter. Questions or comments here?
There's no real difference between the diffraction grating and two-slit equations?
Yeah, so the physical situation is different. Instead of 2 slits, we have thousands of slits, but the effect is the same. It is incredibly small. Yes, it is very small. Modern technology is built on smallness. Has anyone ever held a stick of computer RAM in their hand? it's a few centimeters long, right? Like if you got a PC version that might be 4 or 5 centimeters long.
Ish.
And a typical stick of RAM these days has 8 gigabytes of memory. So think back to when we were talking about circuits, a few weeks ago. We had resistors, inductors, capacitors. The one thing that we didn't get to is transistors. And that's because this class doesn't cover anything that happens after 1910. So transistors are a more modern circuit component that started to become common in the 30s and 40s, so just after the cutoff for this class. Every bit of storage on a RAM requires 3 transistors. That means, so an 8 gigabyte piece of RAM means that you have 64 billion bits of information that it can store, which means there are 180 billion transistors on one stick of computer memory. 180 billion circuit components. They still shouldn't be so expensive. Come on, man, we live in the future. Yeah, you all carry computers in your pocket that are more powerful than what we sent astronauts to the moon with. Anyway, that's a sidetrack. What I meant to say is I meant to give a more modern example. Does anyone know how their cable internet works? Anyone know how you get internet? So if you get cable internet, a fiber optic cable is run up to your house. So this fiber optic cable, the core of it is usually silica quartz. And in the last chapter, we talked about total internal reflection. So if light strikes an interface at too oblique an angle, it just bounces back into the first medium instead of refracting into the second medium. And that's how fiber optic cable works. Light is injected into one end of the cable at an oblique angle. It bounces all the way down the cable till it gets to your house, and there is a device which translates those light signals back into electrical signals, which then are brought into your house via copper wire cabling, or coax cabling. That already is like an enormous technical achievement, enormous achievement of engineering. But it's not enough. Instead, there are actually between 20 and 50 signals traveling through a given piece of fiber optic cable at any given time. And the way that we can get more than one signal down the cable at once is we use different colors of light. Right? And it's not that different color of light. They're all infrared signals, right? So it's all infrared light, but it's a few nanometers different. This is what we call a multiplexed signal. And at the end of the route, when it, before it splits off to go to your house, the signal has to get demultiplexed. And that is a very fancy sounding word, but the way they do it is they stick a diffraction grating on the end of on the end of your fiber optic cable. So here's your fiber optic cable with all your signals coming in. Then there's a diffraction grating on the end of it. And there is a sensor some distance from the diffraction grating. And this sensor will only get bright enough to trip the sensor if a certain wavelength of light hits the grating and gets diffracted up to this point, right? And we know the condition for getting light to diffract up to that point, right? And this sensor right here, that's the sensor that corresponds to your personal internet signal. And there are sensors other places that catch different wavelengths of light, and those are for your neighbors. So if you call up Cox and you say, hey, I want the plan that doubles my internet speed, all they do is they assign you another sensor. And that's how you get faster internet. Hanson, yes, the signals being brought through the fiber are sent as light. No, I want to be green. It's not easy being green, man.
Tell that to Money.
Tell that to Kermit. So, I think this is probably a good point to take a break. And then when we come back, we will talk about thin films and polarized light. So my clock says 12:50 on the nose. So let's stretch our legs and be back here at 1 p.m., 10 minutes from now.